Hello guys, welcome back to my channel Gamma Di Gamma once again. Uh, so in the last video, and please check that out if you haven't already, we talked about the Einstein subscript summation convention. Now I thought to myself before going on to the differential operators and the subscript summation convention on them, let me introduce what multivariable functions are, and then you'll understand what things like the gradient, the divergence, or the curl even mean. So I'm gonna do in these few videos, I'm gonna do a quick crash course on multivariable calculus, at least the multivariable differential calculus. So let's get started. Okay, so let's start with the idea of a regular graph. So I'm sure everyone's worked with a regular graph before. So for regular graph, what did we have? We had the y-axis, which was represented the function of x, and we had an x-axis. And what we did for like single variable functions was we took a point on of x, plugged that into f of x, and then we got some value. We plotted that against x, and we got some fancy curve. The way I like to think about this, because we're going to generalize this for a function of multiple variables. So a function takes input of like two variables, let's say, and gives an output of like, that's basically not a vector. We're going to talk about vector fields a little later, but this function now goes from R2 to R, and what this represents is actually, think about your x and y plane here. So say x-axis, assume this is your y-axis, z-axis is like protruding out. So the xy plane is whatever these two standard basis vectors span. It goes behind the negative region too, but I'm not showing that here. And then when we have a function, what it does, it takes points from the x and y plane, because those were the two inputs that it had, and it returns some scalar value. And I'm emphasizing on scalar now because vector fields are completely different. Scalars just give you information about the magnitude at that point as a function of x and y, not the direction. So you can just represent that with like a collection of points, or you'll have some height, and you can plot that against the points in x and y, and you get this surface. I mean, this drawing is really bad, but I hope you see that. I mean, this is the general notion, because we can see that the single variable function was just a special case of this. We were taking points in x, and then we got information regarding just the magnitude when you took x as the input, and then we denoted that by a collection of points, and that became this curve, this graph of the function. I mean, in this case, I should mention that z is actually denoting function of x and y, For vector fields, however, you still have, say, a function of x and y, but your output is not one dimensional anymore. It's any arbitrary dimension, in this case 2. So in this case, f is going from R2 to R2. And now you don't just have magnitudes at different points for different combinations of x and y, you also have directions associated with them. So the way I could represent this is, for example, this special case here will look something like this. The vectors are radiating out. You need to denote the direction with these arrowheads. And then as you go farther, x and y increase, obviously. So the magnitude increases of the vector. You can think of that as like the length of the vector, or basically the magnitude will be just this, the first component squared plus the second component squared. That increases as you keep on going ahead by increasing x and y. And you denote that by longer arrows. So most of the times it's not convenient for more complicated vector fields, but I hope you get the idea here. It's radiating out basically from the origin. That's how in general vector fields work compared to scalar fields. For scalar fields, your output is always one dimensional. For vector fields, your output is always two dimensional. The difference between vectors and vector fields is that in vectors you have like different components, but each of them is a scalar. In the case of a vector field, however, the component itself is a variable. It's itself a function. That's why you need to do a little more work when you're working with vector fields. That's the thing. We're not going to talk about vector fields much in today's video. We're actually going to focus on scalar fields for now, and how to plot them. Okay, so consider f maps points in R2 to R, so it's a scalar field. You have f of x and y. It's a multivariable function, so it will depend on two things now, not just one. To be square root of x squared plus y squared. First of all, if you want to graph this out, you want to sketch this out, set this equal to z. Z is equal to f of x and y. Now what we can do is we can like take each plane and then look at how this function looks like in each of the planes. So let's first look at the yz plane, and we can do that by setting x to 0. So we simply have the equation z is equal to the absolute value of y. And how does that look like? It looks like this. So if you have your z-axis here, your y-axis here, your x-axis here, I'm maintaining the right hand rule because I don't want the parity to get messed up. And then z is equal to absolute value of y will look something like this. Okay, this is the best I can do. Looks something like this. It's an absolute value in the yz plane. And now let's see what happens in the xz plane. So in the xz plane we have, if you need to look at what the graph looks like, set y is equal to 0, you get z is equal to absolute value of x. So we have a similar thing. It's a little hard to show that relationship here. I won't show it, but it's similar, but in the xz plane though. Okay, but this is not really enough. I mean, just two planes, how the cross section in two planes looks like, it's not really helpful. So what do? What we can do is we can set z equal to 0. So this is the xy plane cross section. When we do that, we have square root of x squared plus y squared is equal to 0, and notice that only one value of x, y and z will satisfy this, which is 0, the origin in R3. Okay, this was just for z is equal to 0. Let's be a little more general. Let's set z is equal to c, x squared plus y squared. Squaring both sides, we have x squared plus y squared is equal to c squared, and c is like a varying parameter because c can be 0 and you have just this first case, c can be 1 and that's basically z is equal to 1. So the xy plane with a constant z is equal to 1, and you can keep increasing c. And what is this? This is a family of circles of radius c. So as you increase your z, the radius of the circles in the xz plane at that z will increase as linearly. So for z is equal to 0, we have 0, so nothing. I'm drawing the x-axis here, the y-axis here. Z-axis here. For z is equal to 0, we just have the origin. Z is equal to 1, we have a unit circle in the xy plane, so it's going to look something like this. Z is equal to 2, we have a circle of radius 2. And then you basically keep on increasing, you get this nice looking pattern. And then I don't know, if you wanna, you can keep increasing c in a continuous fashion or take more samples of c, and you get the cross section you wanted. So this, I'm gonna do like a crude drawing here. So it's gonna look something like this. This is z, and you see these circles of constant z. These are called the level sets. In this case, since this is two-dimensional, these are called level curves. If this were a 3-variable function, we would have level surfaces. So it all depends on what dimension you're in. In general, you call them level sets. And as you can see, they're pretty useful in understanding how the function looks like in the xy plane, and if you change z, what happens. Now I would like to show you the graph of this so that you actually see these things. Okay, lo and behold, the graph of the function we are working with, square root of x squared plus y squared. If you look closely, see we have this tapering profile, this those circles we had that were decreasing in the radius. We have that profile in the xy plane. In this other plane, see we have that absolute value kind of structure. Look at the v there. Similarly here, the v there, So it clearly matches. So it all makes sense. I hope you see how nice this is. Okay, let's look at another function. We have f of x and y is x squared minus y squared, and f again maps points in R2, points in R, again a scalar field of 2-dimension input. Okay, let's look at the profile. So the yz plane, set x to 0, you have z is equal to negative y squared, which basically looks like this. It's not that hard. It's a inverted parabola in the yz plane. Let's see how it's gonna look like. Yup, that is a pretty accurate drawing. And then similarly in the xz plane, set y to 0, we have z is equal to x squared, which is an upright parabola, so it's a little hard to draw here. Let's see. It's a little hard to draw. I think it's not a good idea to actually show that. I'm sure you can see that. You just take the xz plane and then plot it out. If you want me to do it, it's gonna look something like this. It goes like behind it. You see, it was not really clear. Anyways, I'm gonna graph it later, but it's how it's gonna look like. And then if you wanna look at how it looks like in the xy plane, you do this a similar thing as you did for the last time we are working with something like this. Say take c is equal to 1, where z is equal to c. So you have x squared minus y squared is equal to 1, which is a hyperbola. Take the case c is equal to 0, you have x squared minus y squared is equal to 0, which means x is plus or minus y, which is a bunch of lines, 2 lines actually. C is equal to negative 1, and all negatives is y squared minus x squared is equal to 1, again a hyperbola. And to represent all of this, it's going to look something like this. So these are the lines for c is equal to 0, and these are the negative hyperbolas. So it's minus 1, minus 2, minus 1, minus 2. These lines are 0, 0. And then the positive ones are here. 1, 2, 1, 2. So that's what it looks like in the xy plane at least. And now graphing this up, I can do a rough sketch. It's actually going to be a saddle region, a saddle surface. So we have the axis here, x here, and y there. It's going to look something like this. shading some parts out, and then this is like the top part. I'm gonna draw it with like nets. So I hope you kind of see this saddle surface here. It's like going up, down in this xz plane, and then sort of tapering in the yz plane, tapering like downwards in the yz plane. I'm gonna show you anyways. So this is a saddle surface. Okay, so lo and behold, the saddle surface. See what I mean? It's like going like this, like a smiley here in this plane, and then like this plane is like a sad face. So there's like a combination of the smiley and the sad face, and then from this angle you see the hyperbolic profile here, and then these straight lines for passing through the origin. Hyperbolic profile here and hyperbolic profile on the top of this guy. Yeah, so that's how again sketching out different cross sections helps you kind of visualize it. Okay, so one thing to also note is that we were working with functions of two variables that returned a number, a real number. You can also have stuff that is basically of three variables, but it's in the form of an equation. Say like this: x squared plus y squared plus z squared is 1. That's the equation for the unit sphere. The way I like to think about this is there's 3 degrees of freedom, because there's 3 variables, x, y, and z, and 1 constraint, because there's 1 equation that's like sort of restricting them, that the square of x, the square of y, and the square of z should sum up to 1. So that's 1 restriction in the form of this equation. So 3 minus 1, 2. It will be a 2-dimensional surface. It will be a surface basically. All the surfaces are 2-dimensional. And hence it's a sphere in this case. I mean, this logic is sort of what holds for, like, if you're talking about general surfaces in the case of like a manifold. This is a 2 manifold, but I'm not gonna go into the theoretical idea of a manifold right now. And I think everybody knows what a unit sphere looks like. It's centered at the origin. Looks like kind of like this. X, Y, and Z. I'm not gonna show you a graph. Everybody knows how this looks like. Similar to the unit sphere, you can also have a cylinder. X squared plus y squared is equal to 1, for example. But then this will have an infinite an infinite height. If you want to think of z as height, it will have an infinite height but unit radius, because it's 1 here. Again, same logic as the unit sphere. But in this case, you need to specify that this is in R3, or there are 3 variables available to you. Because if you just do this in like regular single variable graphing calculator, this is going to give you a unit circle. we need to ensure that there's a variable available, a degree of freedom in Z available. That's when this will give us a surface, a two-dimensional surface, because by this above logic. So you see how this works. Okay, so let's quickly talk about what limits are. So if you remember in single variable calculus, our limit something like this. This limit existed, if there were two types of limit. There was the left hand limit, right hand limit, and left hand limit was like if you approach a given value from the left hand side, the negative side. Right hand limit was if you approach this from the positive side. And if both of them were same, then the limit in general existed and was equal to whatever value they had. Well, this was the logic, because there were just two directions of approach, like the positive x or the negative x approach direction. If assuming we're calculating our limit at 0, there was no other direction because we were just constrained on the x-axis. But in the case of multivariable functions, so something like this, x comma y tends to a comma b, for example. Now, instead of just having these two directions of approach, well, you have them. You definitely have those two directions. With your y-axis, this is your x. You definitely have those two directions. You can always approach from the positive x and always from the negative x. You can do that with the y, positive y and the negative y. So you have 4 default directions, the directions of the standard bases. But you also have this region between x and y, that x and y are spanning because you're working in this plane. So you also have like this arbitrary direction, for example, of approach. And approach this way, then the negative of that. This direction of approach. Maybe I should use another color here. Let's see. Okay, so you have, say, this direction of approach and then direction opposite to that. This direction of approach, this direction of approach. So it's like your any angle in this xy plane spanned by the axes is a possible direction of approach. So yeah, it's way more complicated, and you can't just rely on whatever we did for single variable calculus. So assume we have a function xy over x squared plus y squared. We need to find the limit as at the origin 0, 0. Well, now notice what we can do is we can first start to approach from the axes. So let's approach from the x-axis, take y is equal to 0, plug that in here. You have limit x goes to 0, y is taken care of, x times 0 over x squared plus 0 squared, which will be 0. Fine. Approach it from the y-axis, along the y-axis. So x is 0. We now have limit y goes to 0. 0 times y over 0 squared plus y squared, which is again 0. So is the limit 0? Because both of these are equal, they're giving 0. But I would also like to point out you can approach along the line y is equal to x, because remember we can approach from any direction. So any direction means a line of any slope. In this case the slope is 1 because y is equal to x. If you do that, substitute all y with x's, just take x as the limit. So x times y will be just x squared because you're doing the substitution, and then 2x squared in the denominator. X's cancel out. and we have 1/2. So look what's happening. If we approach the origin along the axes, we get 0. But if we approach the origin along this line y is equal to x, we get 1/2. So we're getting different values by approaching in different directions, and which means there is some preference for a direction, and that's not how limits are defined. So this limit does not exist because we are getting different values in different directions when we approach the origin. So the condition of just approaching one standard value from the axis is not enough. We need to approach the same value from any direction. Now, for any direction, I mean, here we just knew how to disprove it. We just found one direction and then it wasn't the same, and we knew that the limit did not exist. But in the case of proving that the limit exists, it's a little hard because you need to account for every direction. What you can do is you can also take y is equal to cx, the general equation of a line with slope c. But even that is not really enough because it's not necessary that you approach this point in a linear fashion. You can also approach it in a quadratic fashion. Further examples will show you how approaching in a quadratic fashion is way more different. You can approach in any other fashion. So it's really confusing. So what do? We use polar coordinates. I hope you know how polar coordinates work, because all you need to know is x is r times cosine theta, y is r times sine theta. Because when you do that, what you do is x, y approaching 0, 0. This condition just becomes r approaching 0. Because what you're doing with the polar coordinates, you're setting up like a sort of a circle. Let me use another color here. You're setting up sort of a circle. And as r goes to 0, you're basically shrinking the circle down to the origin, or to the point, the limit point. And since we're using a circle, it naturally takes into account all the directions. So all we need to do is check whether, after using that polar coordinate substitution, if we end up with a theta, because if the r's cancel out, we just end up with a theta, which means it's dependent on a direction or the angle, and hence the limit doesn't exist. But if we have one r, and that r is, like in this case, going to 0, then it exists. So in this case, let's just make that substitution. So if x, y is r squared sine theta cosine theta, x squared plus y squared will naturally become r squared by Pythagoras theorem. Limit as r goes to 0. R's cancel out. We just have sine theta cosine theta, which are independent of r. And this shows that if you choose theta to be, say, pi over 2, you'll have 0. If you choose theta to be pi over 4, you won't have 0. You'll have 1/2. You can check that. So it depends on what theta you're choosing. So which depends on what direction you're choosing. If you're here, if you're going from there, here, which point of entry are you choosing? Hence the limit doesn't exist because it depends on the direction. It's not uniform everywhere. If one r had remained on top, we would have had this entire thing go to 0, and then the limit would exist. Okay, so let's see more examples. Okay, so let's take x cubed plus y cubed over x squared plus y to the 4th. Again, limit at 0. 0 is where stuff gets interesting. Okay, I mean, if you let's just plug in polar coordinates right now. We have r cubed cosine cubed theta plus sine cubed theta, or we can plug out a r squared here, cos squared theta plus r squared sine to the 4th of theta, which cancels out, giving us just a simple expression which is not that hard. if cos squared theta plus r squared sine to the fourth theta. If you take limit as r goes to 0, well, you're just gonna get 0. But I mean, so can we conclude that the limit is uniform because it doesn't depend really on theta? Well, not really. Uh, what we can do is we can be a little naive. We can approach 0 along the y-axis. So take x is 0, and you get 0. I think. Okay, let's actually try to plug this in. If x is 0, we just have limit y is 0, y cubed over y to the fourth, which diverges. Let's approach it along the x-axis. Limit as x goes to 0, x cubed over x squared, which is 0. Well, this should make it clear that we don't even need to do this polar coordinate stuff. We just know that it's not going to exist, because just trying the standard axes, we got different values. We got infinity here, we got 0 here. What you could have also done. See, that's why it's a little misleading using polar coordinates. If the denominator is not x squared plus y squared, using polar coordinates is misleading. What you can do instead of polar coordinates, you can have modified polar coordinates. So instead of y is equal to r sine theta, you can have y squared is equal to r sine theta, such that y to the fourth is r squared sine squared theta, such that x squared plus y to the fourth is r squared. Now this is modified polar coordinates. We plug everything in, we'll have r cubed cosine cubed theta plus r to the 3/2 sine to the 3/2 power theta over, well, let's see, x squared, which is r squared, y to the fourth, which is again r squared. So we have r squared here. Well, if you want, you can do like L'Hopital's or something. But then you notice that like 3/2 is less than 2. So eventually, the limit that r goes to 0 is going to diverge. Although this first term is larger, the second term is smaller, has a smaller power of r, so it's eventually going to diverge. And this is one way of checking whether it will exist or won't exist. Before moving on, I'd just like to show the graph of the two limits we calculated. Okay, so this is the function, the first function we were working with. So, this has the weird shape. Okay, so if we approach from like this side, this way, you reach a 0 because you're going through the valley. Same with like this side, you'll reach 0 because it's like a valley. I think pretty much the same with the x-axis too. You reach a valley, go this way through the valley, or partial valley or whatever, you reach 0. But if you go along in the direction dictated by this plane, like along this plane, you are on the top, you're going through the mountain, and the limit says that since there's like a big discontinuity here, clearly because it's not defined at 0, the limit dictates that it should take the value of half, because it was always taking this top mountain value of half. So the limit along this plane direction says it should be 1/2. So you see the discrepancy. You go through the valley, you get the limit says it should be 0 in that direction. You go through the mountain, the limit says it should be 1/2. And that's why we got different values and the limit didn't exist at 0. For the second function now, And this was our second function. Okay, you see, you approach along like this axis, you reach infinity. See, there's this crazy long spike. You approach from the other axis, you come to 0. See this bridge over here says you should get 0 from this axis. On the other axis, it said you should peak. You should just blast to infinity. See, there's a negative infinity for the negative direction and a positive infinity for the positive direction. And then if you approach along x is equal to y squared, which is basically this blue sort of parabolically folded sheet, approach it along this, you're gonna have something different completely. I think even in this case you're going to diverge because you eventually hit the peak here, so you're eventually going to diverge too, even in this like parabolic direction. So even see, this direction of approach is important because, look at how the structure of this mountain was. It's like, sort of like a bump which has the boundary of this plane that I just drew here, and then there's valleys. So this plane was like, the boundary point, and it was important. So parabolic directions may seem weird, but sometimes functions just have exactly those shaped mountains. So in those cases, yeah, we need to be a little more careful. Let's do like last two. F of x and y is x cubed y over x squared plus y squared. Okay, since we have a nice denominator here, let's go with the polar. Limit it in 0 again. Going with polar, we have r to the 4th cosine cubed theta sine theta divided by r squared. So you lose one r out, 2 r's actually. R squared sine theta cosine cubed theta in the limit will become 0, and it's 0 throughout uniformly. So this limit exists and is 0. See, you see how hard it is for a limit to actually exist in multivariable calculus, because it needs to be the same from whatever direction of approach you take. Okay, we can do the last one. So if you have f of x and y to be x squared y to the 4th over x squared plus y to the 4th squared. Again, the denominator is a little messed up. Let's use some modified polar coordinates here. So limit as r goes to 0, r squared cos squared theta, r squared sine squared theta divided by, well, r to the 4th. You see the r's cancel out, all the powers. You just have cos squared theta sine squared theta, which is dependent on the direction. And another way of showing that this is dependent on a direction and the limit doesn't exist is, well, if you don't believe, or you don't really are comfortable with my modified polar coordinates, then one way of checking that it doesn't exist is, well, approach along the x-axis, take y0, limit x goes to 0, plug in y equals 0, 0 over y to the 8th power, which is 0. Now approach along y is equal to x squared. You have limit as y goes to 0, y to the 8th over 4y to the 8th, and you get 1/4. Both of them are not the same. So it's one way of checking. Let's quickly look at the graphs of both of them so you actually see what's happening. Okay, so for the second last example we worked with, we had this and it existed, this limit existed because, I mean, look at it, look at this nice shape. It's, you go anywhere, you're gonna approach zero. Go from this top, this cliff, these cliffs, you're gonna roll down to zero. It's all nice. There's no like bumps, like these crazy mountains somewhere that look like parabolas, or no, there's no bad behavior. It's a really nice function. And then the last one was, see, this is a little weird. You see, it's hard to see these ridges, but there's these like ridges, like which look like an X, elevated X here, which make it a bad function. And you can see if you approach along x is equal to y squared. Let's plug that in. We can test that. We have that already. So x is equal to y squared. You see, you're going along these small, slightly elevated ridge, and you reach this point here, which is precisely 1/4 as we calculated. So, and then if you go along this axis, you reach zero because you're not on the mountain, you're in the valley. So you see, there's a discrepancy of the limit values, and the limit doesn't exist. Okay, believe it or not, this has been one long video, a really long one, and I hope you really have an intuition of how this stuff works in multivariable calculus. You can practice more examples, you can graph more. I graphed using the grapher on Apple. You can graph on GeoGebra. There's many other, Wolfram Alpha, for example, or even Python, MATLAB, anything. Keep practicing, keep developing an intuition. It's you have to be delicate basically with the limits. You just need to examine a few points, and it's way harder for a limit to actually exist. And it's way easier for it to not exist. So yep. I think that's it for this video, guys. Take care. See you next time and stay tuned. Peace out.